video, we want to learn how to find area between polar curves. The first example is r1 sine of theta. That is a circle with diameter 1 because coefficient of sine is 1, and because it's 1 times sine of theta, it's a circle symmetric respect to the y-axis. The second one, r2, is 1 plus sine of theta. That is a cardioid, again because it's 1 plus sine, it's symmetric with respect to the y-axis. We are looking for area of the shaded region. If you look at the two curves, you see that circle completely is inside the cardioid. When one of the curves is inside the other one approach to find the area between these two curves is to find area of each of them and then subtract. So if I find the area of R1 and area of R2, let's call this 1 and this 2, and then subtract, it's equals to area of shaded region. But the more advanced way that we can apply to any other curve is to look at the curves. Start at theta equals 0 and look at the radius of each curve. The radius of circle, by radius I mean r. R for circle at theta equals 0, it's 0, and for cardioid is 1. When theta is increasing, you see all the time the radius of 1 plus sine, which is the cardioid, is larger than the r from sine of theta or the circle. So you see that always we have r2 greater than or equals to r1. So to find the area, we can use the formula. The formula for finding the area between polar curves is 1/2 integral r2 squared minus r1 squared. Here we have r2 squared minus r1 squared because r2 is larger than r1 all the time. And we take integral from 0 to 2 pi because as you see the shaded region, it's in the first, second, third, and fourth quadrant. At the next step, we want to replace r2 and r1 by the equations. So we have 1/2 integral from 0 to 2 pi, 1 plus sine of theta square minus the square of sine of theta d theta. At the next step, we need to expand 1 plus sine theta. So we have 1 plus sine square plus 2 sine of theta minus sine square. If we simplify, because here we have 1 sine square and 1 negative sine square, then the remaining is 1 plus 2 sine of theta separately. So integral of 1 is theta, and integral of 2 sine theta d theta is -2 cosine of theta. The next step is to plug 0 and 2 pi instead of theta. So first we plug 2 pi. So we have this sentence. 2 pi minus cosine of 2 pi minus 0 instead of theta minus 2 cosine of 0. We know that cosine of 0 and 2 pi is 1. So if we simplify, the final answer is pi. The next example, again, we have two polar curves, one plus sine of theta or r1, that is a cardioid, symmetric respect to the y-axis because it's 1 plus sine, and r2 is cosine of theta, again because coefficient of cosine is 1. It's a circle with diameter 1 and symmetric with respect to the x-axis because it's cosine of theta. We're looking for area of shaded region inside the cardioid and outside the circle. So you see that some part is in the first quadrant, and in the first quadrant we have graph of r1 and r2, both of them. And if you look, when theta is increasing from 0 to pi half, always r1, the radius of 1 plus sine, is greater than r2. So when theta is between 0 and pi half in the first quadrant, r1 always is greater than r2. And then we have some region in the second quadrant that belongs to only r1 or 1 plus sine. So when theta is between pi half and pi in the second quadrant, we have area of r1 only. In some region, it's in the third quadrant and only for graph of r1. So when theta is between pi and 3 pi half, again, the only curve is r1. And in the fourth quadrant, as you see, there isn't any shaded region. So to find the overall area, we can take difference between r1 and r2, and then take integral from pi half to 3 pi half from r1. So the formula is integral from 0 to pi half in the first quadrant, subtraction of square of r1 and square of r2. r1 is 1 plus sine and r2 is cosine. We know that r1 is larger. And then integral of r1 square from pi half to 3 pi half. Now let's replace r1 and r2 by their equations. Okay, r1 is 1 plus sine and r2 is cosine of theta. So the next step is to expand 1 plus sine in both integrals and gives us 1 plus sine squared plus 2 sine of theta. Now let's simplify because we have positive sine squared and a negative cosine square. By simplify, I mean instead of sine and cosine square, because we cannot take integral, we need to replace them by 1/2 times 1 minus cosine of 2 theta for sine square, and 1/2 times 1 plus cosine of 2 theta for cosine square, as you see. Now, if we distribute 1/2 to the parentheses, and again 1/2 to the second parentheses, you see that some terms cancel each other. Here, positive and negative 1/2. And the remaining part is 1 minus cosine of 2 theta plus 2 sine of theta d theta from 0 to pi ½ and 3/2 minus 1/2 cosine 2 theta d theta from pi½ to 3 pi². Now let's integral from each term separately. So we have these three terms for the first integral. Integral of 2 sine is negative 2 cosine. And these two terms for the second integral. Now we plug endpoints, pi½ and 0 for the first, pi½ and 3 pi½ for the second integrals. After simplification and considering sine of pi, cosine of pi½ cosine of 0, sine of 3 pi, the final answer is pi plus 1. That's the area between our curves inside the cardioid and outside the circle. The next example, we have two polar curves. R1 is 3. It's a circle with radius 3. And R2 is 3 times cosine of 3 theta. Because we have cosine of 3 theta, so we have a rose with 3 petals, because the coefficient of theta is odd, so we have 3 petals. And we're looking for the area inside the circle, outside the rose. As you see, this area, it's in the first, some part of them it's in the second, some part in the third, and some part it's in the fourth quadrant. So we should integral from 0 to 2 pi. Let's find area of each of them separately, because rose is completely inside the circle. Area of the circle, it's 1/2 integral of r1 square d theta from 0 to 2 pi, because the shaded area, as you see, it's in all quadrants, so it's from 0 to 2 pi. And then we calculate the area of rose. Let's call it 2. So it's 1/2 integral again from 0 to 2 pi r2 square d theta. Now let's find each of them, calculate 1 and 2 separately, and then find the difference between these two. So area of circle, it's 1/2 integral from 0 to 2 pi 9d theta. It's 9 pi. And the integral of rose is area of rows is integral from 0 to pi. Our function is 3 cosine of 3 theta. So the square is 9 cosine square of 3 theta, d theta. 9 is a constant, so let's pull it out. We have 9 half integral from 0 to 2 pi. And because here we have cosine square, and you remember that we don't have a direct formula, we replace it by 1/2 times 1 plus cosine of 2 times the angle. The angle here is 3 theta. Let's multiply 1/2 by 9/2. So we have 9/4 integral from 0 to 2 pi, and 1 plus cosine of 6 theta d theta. Let's take the integral from each of them separately. Integral of 1 d theta is theta, and integral of cosine of 6 theta is 1 over 6 sine of 6 theta. And for the next step, we plug 2 pi and 0. 6 times 2 pi is 12 pi, and then subtract. Now we plug 0 instead of theta. So we have sine of 0, sine of 0 and sine of 2 pi, both of them are 0. So the only remaining part is 2 pi times 9/4. That's equals to 9 pi half. This is the area of the rows. We also calculated the area of the circle. Now let's subtract these two to find the area of shaded region. Area of circle is 9 pi, and area of rows is 9 pi half. So the answer is 9 pi half. Okay, that's all about the finding the area between polar curves. I hope these examples have made things more clear for you.